Training large language models, LLMs, for program synthesis tasks is a complex and computationally expensive endeavor. The choice between bidirectional and unidirectional representations, the lack of unification in synthesis and understanding tasks, and the significant compute requirements all pose significant challenges. To address these challenges, researchers propose a unified approach, developing a single prefix-LM model that combines both encoder and decoder-based models. A novel learning algorithm is also introduced, incorporating causal language modeling, span corruption, and infilling. Furthermore, the free lunch hypothesis for infill sampling is explored, and the impact of mixture distributions and multi-epoch training on model performance is examined. Through a series of empirical experiments on 1B LLMs, 5 key lessons for practitioners are derived, highlighting successful and unsuccessful attempts at optimizing the training process. The authors provide a recipe for training CodeGen2 models in sizes 1B, 3.7B, 7B, and 16B parameters, accompanied by an open-source training framework. This work contributes to the ongoing research on neural scaling laws, which dictate the performance of LLMs as a function of model parameters, data, and compute. By identifying unresolved challenges and proposing solutions, the authors aim to reduce the monetary cost associated with exploring different model architectures, learning algorithms, and data distributions, ultimately making the training of LLMs for program synthesis more efficient and cost-effective. The paper introduces a unified approach to training large language models, LLMs, that can effectively perform both synthesis and understanding tasks. It explores the unification of model architecture, learning objectives, sampling procedures, and data distributions. The proposed model is based on the prefix-LM architecture, which integrates encoder and decoder representations into a single model. A mixed learning objective combines causal language modeling and span corruption for efficient information transport in zero-shot learning and understanding tasks. The paper also discusses the use of both left-to-right and infill sampling, assuming the free lunch hypothesis, where equipping a model with infill sampling does not increase computational cost. However, the findings indicate that this hypothesis may not hold true, as the addition of infill sampling incurs an additional cost in compute. Moreover, the paper explores the mixing of natural and programming languages into a single model, showing promising results for multi-epoch training. Despite not achieving full unification, the paper provides valuable insights and trained competitive open-source models on permissive data. The contributions of the paper include 5 lessons distilled from the results: a simple unified mixture of uncorrupted and within-file span corruption sequences with next token prediction, an open-source implementation for LLM training, and open-source models in the CodeGen2 family trained solely on permissive data. This section of the paper discusses related work and introduces the methodology for the proposed approach. The authors first discuss the use of large language models, LLMs, on code transformers, which capture dependencies among sequence elements through attention mechanisms. These models have been shown to be highly scalable in natural language processing tasks. Several efforts have explored the use of these models for program synthesis, including works by Chen et al., Austin et al., Li et al., Fried et al., Nijkamp et al., and Allel et al. The effectiveness of these models has been evaluated in various studies, such as Vaithilingam et al. The authors then discuss ablation studies, highlighting the work of Raffel et al., who introduced the concept of a non-causal decoder in the form of a prefix-LM. This prefix-LM has been shown to exhibit favorable performance over causal decoders after fine-tuning on downstream tasks. However, its performance in few-shot generative tasks was not evaluated. Wang et al. Conducted an extensive ablation study over architectures and objectives, concluding that decoder-only models with causal language modeling exhibit the strongest zero-shot generalization. Tay et al. Compared encoder-decoder, decoder-only, and prefix-LM architectures, reporting the beneficial performance of encoder-decoder models, although zero-shot generation tasks were not evaluated. The authors also discuss data mixtures, citing the example of Lambda, which was trained on a mixture of various data sources, including dialogues, code documents, Q&A data, tutorials, and Wikipedia. However, the impact of this mixture and the specific sources used are unclear. Xie et al. Introduced a data selection method based on importance resampling, allowing the mixing of datasets of various sizes. The methodology section begins by defining the requirements for the proposed approach, including performance on a variety of tasks. The authors aim to unify learning methods and model architectures while maintaining or improving performance on individual tasks under an identical compute budget. The tasks considered include program synthesis with left-to-right sampling, zero-shot, program synthesis with infill sampling, zero-shot, in-context learning from examples, few-shot, and program understanding with bidirectional representations, fine-tune. Specifically, the authors consider 4 tasks: program synthesis with left-to-right sampling, program synthesis with infill sampling, in-context learning from examples, and program understanding with bidirectional representations. For program synthesis with left-to-right sampling, the prompt is in the form of a function signature and docstring, and a program is conditionally sampled based on the prompt in left-to-right autoregressive fashion. The human eval benchmark is used to evaluate the quality of synthesized programs. For program synthesis with infill sampling, the prompt includes both past and future tokens for which the tokens, in between, are supposed to be sampled. The human eval infill benchmark is used for evaluation. For in-context learning from examples, a task is defined given a set of examples, and the goal is to sample a label based on the provided examples. The X-sum benchmark is used for evaluation. For program understanding with bidirectional representations, the goal is to obtain representations that can be a function of all input tokens simultaneously, which is desirable for understanding tasks such as defect detection. The code-XGLUE and superglue benchmarks are used for evaluation. The authors note that they limit their investigation to causal and non-causal decoders, as well as encoder-decoder and prefix-LM architectures, based on the results of the ablation studies. A unified language model is proposed, integrating architecture, objectives, sampling procedures, and data distribution. The model architecture is based on prefix-based language modeling, prefix-LM, combining bidirectional and unidirectional attention mechanisms. This approach enables contextualization between tokens in the prefix and context parts of the input sequence, unifying the benefits of encoder and decoder-based models. The learning algorithm is a mixture of causal language modeling objectives and span corruption, aiming to minimize task-specific prior information to avoid overfitting. This mixture includes uniform distributions over mixture ratio of tasks, length of prefixes, and length of spans. The proposed algorithm mitigates overfitting by introducing randomness in the sampling process. For sampling, a multi-turn conversational scheme is employed, similar to previous works, but without explicit instruction fine-tuning. This approach hypothesizes that the emergence of few-shot abilities in language models can be attributed to weak supervision in the data, where programs often include functions with accompanying English descriptions. To enhance the model's performance on downstream tasks in both natural and programming languages, the authors propose increasing the amount of natural language in the data distribution. This unified language model is expected to be competitive on various tasks, leveraging the strengths of both encoder and decoder architectures. By integrating these components, the model can effectively handle diverse tasks and languages, making it a robust and versatile language model. The authors present the empirical results and conclusions of their attempt to unify and ablate prefix-LM, a model that combines the benefits of both encoder and decoder architectures. The findings are distilled into 5 key lessons, which are discussed in this section. The first lesson questions the benefits of prefix-LM's unified architecture. The model behaves as an encoder with bidirectional attention and as an autoregressive decoder with a causal mask. However, it is unclear whether this unification leads to competitive performance on both ends. The authors evaluate this question from 3 angles: data, representation, and objective. In terms of data, the authors investigate whether the prefix mask negatively impacts the learning of prefix-LM. They hypothesize that the lack of gradient on the non-causal part of the sequence results in worse results on the code generation task. To test this hypothesis, they train a prefix-LM on Big Python and compare its performance on human eval against a causal decoder baseline. Surprisingly, they find that the human eval scores for prefix-LM are on par with the causal decoder for the majority of pre-training. However, when repeating the experiment on the stack dataset, they observe strictly worse throughout the pre-training, resulting in a 2-point worse performance than the causal decoder baseline. In terms of representation, the authors investigate whether the bidirectional attention in prefix-LM allows for competitive encoder representations that can be used for a range of discriminative tasks while retaining generative capability as the decoder. They train prefix-LM with a mixture of causal language modeling and span corruption and evaluate its performance on the defect detection task from CodeGen2 and 4 tasks from superglue. The results show that prefix-LM yields competitive encoder representations that can be used for a range of discriminative tasks while retaining generative capability as the decoder. Overall, the authors conclude that the benefits of prefix-LM's unified architecture are questionable, and that the lack of gradient on the non-causal part of the sequence may negatively impact the learning of prefix-LM. However, they also show that prefix-LM can yield competitive encoder representations that can be used for a range of discriminative tasks while retaining generative capability as the decoder. This research delves into the development of a novel model called prefix-LM, which leverages bidirectional attention for both encoding and decoding tasks. The authors compare its performance with causal decoder models on various programming language understanding tasks such as human eval and CodeGen2. The results indicate that prefix-LM generally achieves better performance over causal decoders when trained with the same objective, suggesting that bidirectional attention can yield informative representations. However, the authors also find that their 1B parameter model fails to outperform smaller-scale encoder-only pre-trained models like CodeBERT on CodeGen2 or RobertLarge on superglue, implying that the representations generated by prefix-LM are not sufficiently informative to justify replacing smaller-scale models. The study also investigates the effectiveness of the UL2 objective, a combination of causal language modeling and denoising with 6 different hyperparameters, as proposed by Tay et al. 2022a. Although this objective has shown significant gains in other domains, the authors observe that it underperforms compared to the CLM baseline in the programming language domain, particularly on human eval. They hypothesize that this could be due to the small ratio of non-corrupted sequences used in one of the UL2 objectives, sdenoiser. To verify this hypothesis, the authors adjust the sdenoiser hyperparameters to increase the percentage of sdenoiser from 14% to 50% and shorten the average prefix length from 75% to 50%. This modification leads to consistent improvement on human eval over the original UL2 hyperparameters. The authors conclude that causal language modeling on non-corrupted sequences aligns well with the zero-shot generation task in human eval, which requires sampling at the end of the prefix. Therefore, they maximize the number of tokens in the sequence used for gradient updates to learn a competitive model. Furthermore, the research examines the concept of infill, the ability of a model to edit tokens within a file, not just at the end. Bavarian et al. 2022 suggest that infill can be achieved without degradation in left-to-right sampling at the end of context by carefully permuting a portion of sequences from training data, making infill for free. However, concurrent work by Allel et al. 2023 reports a consistent performance drop in left-to-right sampling in human eval when the model is trained on the infilling objective. The authors aim to verify the free lunch hypothesis by training a causal decoder with a mixture of CLM and PSM, prefix, suffix, middle sequence reordering, infilling objective, following Bavarian et al. 2022. This research paper introduces CodeGen2, a competitive, multilingual, and versatile language model trained on a subset of the stack version 1.1 dataset. The model's architecture is designed to learn both left-to-right and infill sampling capabilities simultaneously, using a mixed objective that combines span corruption and causal language modeling. This approach ensures that document boundaries are not accidentally masked during span corruption, resulting in well-formed contexts for the model to process. The authors compare their approach with the prefix-LM model, highlighting the limitations of the latter in terms of multilingual performance and utility of representations. They also address the issue of infill not being for free, as observed in previous studies, by carefully choosing the objective and corruption methods. The paper presents 4 model sizes 1B, 3.7B, 7B, and 16B and evaluates them on various tasks such as human eval infill, XSum, superglue, and code-XGlue. The results show that the CodeGen2 model outperforms the prefix-LM model in most tasks, demonstrating its effectiveness in learning both left-to-right and infill sampling capabilities. Moreover, the paper emphasizes the importance of selecting a suitable objective and corruption method for training a versatile language model. It suggests that a simple yet carefully chosen objective can be more effective than complex ones, as seen in the case of span corruption and mixed objectives used in CodeGen2. In conclusion, this paper contributes to the ongoing research in developing multilingual, versatile language models capable of handling both left-to-right and infill sampling tasks. The proposed approach, CodeGen2, offers a competitive solution that aligns with the growing interest in cross-modal applications between natural and programming languages. A recent study explores the training of a large language model for code, focusing on its ability to generate code from text. The authors hypothesize that the model's poor performance on natural language tasks can be improved by leveraging a sufficient learning signal from a distribution of natural language. To test this, they train a causal decoder using a combined objective of causal language modeling and span corruption on a mixture of natural and programming languages, dubbed mix. The model is evaluated in a zero-shot manner on both programming and natural language downstream tasks across training steps to assess the effect of data mixing on each modality. The results are compared to 2 baselines. One trained solely on the pile, natural language, and another on the stack, programming language. Although the mixed model does not outperform the baselines for the evaluated tasks under the same compute budget, it performs closely to the domain-matched models and substantially improves performance over the domain-mismatched baselines. This suggests that mixing natural and programming languages can be beneficial when the compute budget is constrained and the resulting model is used for both domains. The authors also discuss the potential of multi-epoch training, as the increase in model size is bound due to the common practice of pre-training the model for only one epoch. They hypothesize that the model has the capacity to absorb information from repeated observations, and further experiments are needed to explore this possibility. The authors present results from training a 7B parameter model, referred to as CodeGen 2.5, with the CodeGen2 objective on repeated star-coder data, a multilingual programming language dataset containing commits and issues. This dataset consists of 1.4 trillion tokens, equivalent to 5 epochs. Despite not being exposed to new data after 280B tokens, multi-epoch training continues to improve program synthesis capability. Comparative results are shown in Table 3, comparing the CodeGen 2.5 model to the baseline CodeGen 27B model trained for 400B tokens. These results highlight the importance of exploring individual contributions of factors such as increased token budget, span corruption as a form of data augmentation, and higher learning rates over a longer period. The authors conclude that while they did not achieve satisfactory unification across architecture, objectives, sampling procedures, and data distributions, their findings and final training recipe may be valuable for practitioners. They distill their hypotheses into 5 lessons, including the ineffectiveness of the prefix-LM architecture, the challenges of training with infill sampling, the sufficiency of a simple mixture of causal language modeling and span corruption limited to within-file spans, the promise of a mixture distribution of programming in natural languages, and the strong evidence for the effectiveness of multi-epoch training. To facilitate future research, the authors plan to open-source the training implementation and the resulting family of CodeGen2 models with varying parameter sizes. StarCoder, a large language model, is designed to efficiently train and generate code snippets. Building upon previous studies such as BERT, GLM, and encoder, the authors leverage large datasets like the pile and the stack for pre-training. The primary focus is on code infilling, where the model fills in missing parts of code based on context, requiring an understanding of both natural language and programming syntax. To achieve this, the authors propose a novel pre-training objective called middle filling, where the model predicts missing tokens in a sequence, whether code or natural language. StarCoder is trained on a combination of natural language and code datasets to achieve strong performance on both tasks. The architecture is based on transformer layers, similar to state-of-the-art language models, but with the key innovation of learning from diverse data sources, including code repositories and natural language texts. Evaluation methods assess the model's performance on various benchmarks, including code generation and natural language understanding tasks. The results show that StarCoder outperforms existing models in terms of accuracy and efficiency, demonstrating the effectiveness of the middle filling objective and the importance of multimodal pre-training. By leveraging large datasets and novel pre-training objectives, StarCoder presents a significant advancement in language models, particularly in understanding and generating code. This work has implications for future research in natural language processing, programming languages, and artificial intelligence. Please provide the original text you would like me to refine. I'll transform it into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, while following the guidelines you provided. The development of large language models has led to emergent abilities, as demonstrated by Jason Wei et al. In their 2023 ICLR conference paper. This work showcases the capabilities of large language models in various tasks, setting the stage for the current research. Moreover, the importance of data selection in fine-tuning language models is highlighted by Michael Xie et al.'s 2023 ArXiv preprint, which presents a methodology for selecting informative data points via importance resampling. These foundational works establish the basis for the author's contributions, which aim to improve language model training through novel data selection and optimization techniques. By building upon the understanding of large language models' emergent abilities and the importance of data selection, the author's approach positions itself as a natural extension of existing knowledge. The author's awareness of the current state of research in the field is demonstrated through these citations, providing a foundation for potential future work that could further explore the interplay between large language models, data selection, and optimization techniques. The current research's focus on optimizing language model training through novel data selection and optimization techniques is thus situated within the broader context of advancing the field of large language models.